So we're gonna start. So in this unit, we're gonna be mostly talking about the probability and statistics about gases, but the we just need to start with a little bit of regular probability with things that we're familiar with. Thinking about probability. And I'm putting microstates and macrostates here because that's kind of the terminology that we need to get used to. And to be honest, statistical physics or statistical mechanics was always my least favorite class when I took it, both as an undergrad and a grad student. But then when I went back to teach it, I started to really see just kind of the importance, or it's kind of mind-blowing to me because it's all just about large numbers and that they tend to converge. We don't have to think about forces or anything like that. Okay, so let's start with the experiment. So take your coin. Hopefully you have a notepad or something to write down. So flip it 10 times and record the full sequence, heads and tails. So, I have one. Well, I can go ahead and show you mine. So H, 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 T, H. So go ahead and do that, and then I'll have you one by one read your sequence to me, and I'll record that here. All right, so whoever gets done first, you can go ahead and unmute yourself and let me know your results.
I got tails, tails, heads, 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 and then tails, tails, and then heads, heads.
Okay, and did you count that up?
Hmm?
How many heads? Sorry, is that 5?
There were 3. There were 2 T's and then 3 heads.
Yeah, no, I got the whole sequence there.
Yeah.
Wait. T T T H H H T T H H.
Yeah.
Is that right? Okay, so that's 5 heads, I think, if I counted that right. All right. Who else? Who's next?
So I have heads, heads, heads.
All right.
Jarrett. This is Jarrett. This is Jarrett.
Josh.
Okay.
Then tails.
Tails.
Heads.
Heads.
Tails. Heads. 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 Tails.
All right, and so that is 7 heads.
Yeah.
All right, who's next?
Go next.
All right, Ahmad.
Heads, tails, 3 heads.
Okay.
And then tails. And then all of them, the rest of them are heads.
All right, so
there should be 8.
8 heads, okay. All right, Travis.
I got tails, tails, heads, tails, heads, tails, heads, tails, and then tails, head.
So that is 1, 2, 3, 4 heads. All right, and Victoria?
I got heads, heads, tails, heads, tails, tails, heads, tails, heads, heads. So 6 heads.
Okay. All right, so the question that I pose here is, do any of these sequences seem more or less likely than the others? What do you think?
I mean, mine does
Seems
seem more likely
more likely?
because I have 8 heads than tails.
So you'd expect, so more likely means what you would expect.
Oh yeah, I mean like I would expect heads like any flip I do. Let's say more.
So okay, so that's a different question,
Oh,
right? So you're saying if you kept flipping, if you flipped this head thing 10 more times, you'd expect to get a lot of heads again.
probably.
Okay,
Maybe.
but if we just start, okay, so I mean, hopefully your coin would be fair, right? So for any given flip, you would expect heads or tails, right? So if you just ask somebody, if I flip a coin 10 times, how many heads would you expect? 5, right?
5, yeah.
Yeah. So you might be tempted to say that Mallory's here is a more likely result, right? Or it doesn't seem that weird. Or maybe Mallory's is also kind of weird because you got 3 tails, 3 heads, 2 tails, 2 heads. I don't know. But so the question of how many heads you would expect is different from, is this sequence of heads and tails more likely than that sequence of heads and tails? So each of these sequences is what we call a microstate. But if we count the number of heads, that's a macro state, right? So here, okay, among us, we've got 60 coin flips. And let's see if I can sum this real quick. We've got 13, 21, 28, 32, 38, right? So we got 38 heads versus 22 tails, right? So somewhat of an imbalance. Now, some of that might be thrown off by a coin flip not being really random. If whatever side you leave up is going to be more likely to end up with that side up, but should be more or less fair. So here's a quote. If you can't see the whole thing, you can minimize or move the videos. But this is a quote from Richard Feynman when he was giving a talk on, I don't know, he was talking about probability. He said, the most amazing thing happened to me tonight. I saw a car with the license plate ARW357. Of all the millions of license plates in the state, what was the chance that I would see that particular one tonight? Amazing. Right. So the point of this is like, yeah, it's extremely random, and like to see that particular, I mean, if we all, well, we shouldn't go outside, but if we all went out and just looked at license plates and I gave you something, okay, that one doesn't fit Indiana's if you're in Indiana, or I don't think it fits California either. But seeing a particular license plate is not all that surprising. Right. So the point being, and this is sort of the fundamental truth of statistical physics, all microstates are equally probable, right? So any sequence of coin flips would be equally probable. So if we go back to our, so saying heads, tails, heads, tails, heads is just as probable as tails, heads, tails, heads, right? Even though one ends up with what seems to be the more unlikely event, or is the more unlikely event of 8 heads, if we did this more than six times. So we can also see, in small numbers, you get weird fluctuations from what you would expect that average to be. Okay, so each of these sequences is just as likely. And if we flipped the coin 1,000 times, we would expect to get a lot more closer to that central distribution, right, of 500 heads versus being far off from that. Okay, so all microstates are equally probable. It's the macro states that describe a distribution. So how do we talk about this mathematically, right? So why is 5 heads actually the most probable, assuming that your coin is a fair coin? And so we have a terminology here that we say that macro state has the biggest multiplicity, right? So the state of having 5 heads has the most possible different arrangements, the most possible different sequences that add up to it, right? So you can, the easiest example to think of is, well, how many different ways would there to be get 10 heads? Only one, right? There's only one possible way. You'd have to flip heads, 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 right, 10 times in a row. So if the multiplicity is the terminology for how many microstates have that particular value for the macro state, right? So the total number of microstates for 10 coin flips is going to be 2 to the 10th, right? You have 10 different things, each of which can have 2 different values. So that's 1,024, right? So the probability of getting 10 heads is going to be 1 out of 1,024, which is less than 0.1%. But how many, if we wanted to say what's the probability of getting 2 heads? Well, what we should do is calculate how many microstates have 2 heads, how many different sequences would give us exactly 2 heads, and divide that by 1,024. Right, so again, you might want to move the videos out of the way if it's still showing for you. But what we would say is, okay, how many, so rather than thinking of these things in order, happening one after another, think about putting 10 coins in a row, right, just in front of you. Now, how would you get, if you wanted to say, okay, how many different ways could I have 2 of those be heads, right? So put them all down as tails, and then say I'm going to pick 2 of these and flip them over, right? So when you flip the first one, you would say, well, I've got 10 different choices of coins that I could flip, right? So that's 10. And then now that I flipped one, if I'm going to flip a second one, I've got 9 different coins to choose from. All right, so let's say arbitrarily, you pick the one that's all the way to the left and then the one that's all the way to the right. Well, so then you end up with, heads, tails, 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 heads, right? But the fact that you flipped this one over first and then this one over doesn't make it any different. So I have to say, well, I can divide that by the number of possible orderings, right? I could have done it this way and then that way. So that's going to be 10 choices. 10 choices for the first one to flip to make heads, 9 choices for the second one to flip, and then divide that by the number of possible ways I could have done that. I want to say, so that's going to be what? 45. 10 times 9 divided by 2 is 45 different ways, right? So 45 divided by 1,024 is going to be like 4%, right? The odds of getting exactly 2 heads. If we wanted to say 3 heads, then we'd say, okay, I've got 10 choices for the first coin, 9 choices for the second coin, 8 choices for the third coin. But then the possible orderings are, well, which one went first? I've got 3 different ways. And then for each one of those, which one went second? I've got 2 different ways. And then I'm forced to pick the third one. Right, so there would be 10 times 9 times 8 on the top, divided by 6 different possible orderings of doing that. Right, so this is, well, I'll define on the next slide, but this is a field of probability that's called combinatorics, and this this choice here is what's called, or it's said, as you've got 10 to choose, 10 choose 3, right? Would be the 3 heads. And it would be the same multiplicity as 3 tails in this case, because there's only 2 options. Right, so, okay, how do I make a general formula for that? Well, I can see that, like, on the top, I'm going start, 10 times 9 times 8, and then I stop after I've done 3 of those, however many I'm picking. And then on the bottom, I start from 3 and multiply down 3, 2, 1. Right? So this is where remembering things about factorials comes in handy. Okay, so making this more general. So if I have, so omega is the multiplicity of, so I have 10 coins, choose n of them to be heads. Right, I would say 10 times 9 times, and then I go down until I get to 10 minus n plus 1. And then on the bottom, I do n times n minus 1 times n minus 2 down times 2 times 1. Right, so now factorial is you start with the number and you multiply it by all the integers smaller than that until you get to 1. So we can simplify this and write everything in terms of factorials with, so if we have big N number of different things and we're choosing small n out of them, then we can write the formula like this. So big N factorial divided by little n factorial multiplied by the difference factorial. And the notation for big N choose little n is that parentheses thing, right? So it's not a fraction, it's a combinatorics notation. So if you did that for, and I didn't actually plot this distribution, but if you, okay, so we found that there was, there's only one way to get exactly 1 heads or 1 tails, or sorry, 0 heads or 0 tails. Yeah. And then there were 45 ways to get, well, I skipped 1 heads, right? So there's 10 ways to get 1 head. There's 45 ways to get 2 heads, so on. We would see that it peaks at 5 and then starts going back down again, right? So you get this symmetric distribution. The most likely one is 5. Any questions about that so far? Okay, so that's just, coins. You can say, well, that's a really simple system, right? There's only 2 options. How could that be, related to something that's supposed to describe thermodynamics? Oh, I meant to make this appear one at a time, but so hopefully you're not overwhelmed here. So to start with something really simple, right? Because gases, when we talk about gas, we have to worry about the fact that the molecules, not only can they have different energies, but they can also move around, right? So let's start out just with a really simplistic version of a solid, right? So a solid is made out of n different oscillators, right? So an oscillator just meaning like an atom or a molecule, right? So that atom or that molecule, we don't have to worry about the specifics of it. We're physicists, so we treat everything as if it's a harmonic oscillator anyway, right? So if you have a harmonic oscillator and you put a little bit of energy in it, 1 energy unit in it, if you put a second one on top, well, those are going to be evenly spaced. If you remember from quantum mechanics, right, the energy levels are evenly spaced. So if we have n different molecules, whatever they are, and we have q different units of energy to distribute around them, we can, okay, let's just make it concrete. So if we look at the bottom, if we have 8 different energy units and 4 different oscillators to put that in, a microstate could be, okay, put 2 units of energy in each of the 4 oscillators, right? Or I could, have one of those is going to have 3, one of them has 1, and then the others have 2, right? Whatever combination, any combination is allowed. You're even allowed to have all 8 units of energy be in a single oscillator, right? So those microstates, those arrangements are all equally probable, right? So that's our assumption. Now we can say that from a macro perspective, you're probably not going to end up with all the energy in a single oscillator. That seems unlikely based on our everyday experience, and you'd be right. Okay, so we can say any oscillator can have any number of heat units from 0 to Q. So from none of it to all of it. So if I wanted to say, well, what's the multiplicity, right? The number of different ways to arrange that with n different oscillators and q amounts of heat energy. It's given by, okay, so our total things that we have to pick from is now actually q plus n minus 1. Now that seems a little bit, where would we pick that out of? But I think this picture down at the bottom with the symbols helps us kind of visualize how this follows the same math as the coin flips, right? So in the picture down at the bottom, so there's 8 dots. Those represent our units of energy. And then the vertical lines represent dividers between the oscillators, right? So in this picture, we've got one oscillator. The oscillator on the left has 1 energy unit. Then the next one has 3 energy units. Then the next one has 0, and the last one has 4. Right? Okay, so now kind of abstract from there, right? How can we, I could change this to any of the other different microstates by just moving those lines around, right? So I have 8 dots for 8 symbols that represent heat, and then 3 symbols, n minus 1, that represent the divisions between oscillators, right? So that's why, so I could say it's kind of like having 12 coins and saying 3 of them are tails, or in this case 8 of them are heads, right, where we say Q. Okay, so that's kind of the proof just by looking at symbols why, even though this seems much more complicated, right? I've got a bunch of different bins that I can put a bunch of different items in, right? That seems more complicated mathematically than just flipping a bunch of coins that can only either be heads or tails. But we can make the math look exactly the same as what we just proved for coins, and we can use the same math. Okay, so that's something that I don't want you to focus too much on calculating all these multiplicities and stuff, but just getting an idea of, okay, we can do this just with the simplest, what are the odds of flipping five heads versus 5 tails kind of math probability. So so now let's look at interacting systems rather than just a single the videos rather than just a single solid. What if we had 2 different solids that can exchange energy between each other? Well, in that case, okay, so in this really simple one, we've got 6 units of energy, and then each of our solids has 3 different oscillators in it. Right, so what we would do is first say, okay, look, if you look at the first line of the table, it's saying how many different ways are there to put 0 units of energy in solid A? There's only one way to arrange them within solid A, but if you take those 6 units and rearrange them all the different ways in solid B, you'd have 28 different ways over there, right? So you've got one way to arrange what's here, 28 ways over there. So the total number of arrangements is multiply the 2 together, you get 28, right? But now if I take one of those units from B and put it into A, then there's 3 ways to arrange it within A, 21 ways to arrange it within B, multiply those 2 together, you get 63. Right, and you just, so within each one, so for each line of that, you would have to do 2 different calculations of multiplicities using the formula we had before, and then multiply them together. So you could see, okay, there's 28 different ways to put all of the energy in one, or in solid B, but there's 100 different ways if you share the energy equally. Right, so it's more probable to have the energy shared equally. It's slightly less probable to have like 1 extra in one side versus the other side, but not that big of a difference in probability. Right, but the idea of all these microstates are equally accessible. All these microstates just kind of randomly. They randomly share energy between each other. If we started out with all of the energy in solid B and then looked at it at some random time later, we would expect there to be more energy, for energy to have moved from solid B to solid A. So the idea that energy flows from hot objects to cold objects, there doesn't need to be any kind of force, right? There's no force being described here. It's just random transfer of energy and the fact that it's more probable for it to be shared more evenly. Okay, so that may be not that impressive with those numbers, but let's kick it up a notch to 100 units of energy. Now here in the textbook I took this from, they decided to make it uneven, the sizes, right? So object A now has 300 oscillators, and object B only has 200. So A is just a bigger object, right? It's 50% bigger. Sorry, trying to move my videos again, but I can't see my cursor. There we go. Okay, so here again, we see that if you put all of the energy in object B, there's only one way to rearrange it within object A, but there's 10 to the 81 ways to do it within object B. That seems like a really big number, right? A lot of different ways to rearrange it within object B. But if you look at the place where it's most probable for for A to have 60 of these units and B to have 40, right? And the reason why it's not even is because they're not the same size. That's 10 to the 114th. Right, so even though there's a lot of ways to have all the energy be in one unit, or sorry, one object, seems kind of surprising, but 10 to the 81 is really small compared to 10 to the 114. Right, so 33 orders of magnitude. Right, so the probability of being away from that is really small unless it was set up that way to start with. And if we did set it up with all the energy in object B to start, we would, and looked at it at some random later time, we would definitely find it near the center of that peak, right? Near the point where the energy distribution relates to the size of the objects. Yeah, and even going one off, right? 6.9 times 10 to the 114th versus 6.8 times 10 to the 114th. Now that's not that much of a difference, but it's still, it's still fairly big. But in terms of a ratio, it's whatever 6.9 divided by 6.8 is, right? Not that big, but less, like about a 10% difference. And so, if you started in that likely position, you're never going to see stuff move to the other side, right? So, there's a famous quote about, like, if you had a million monkeys banging on a million typewriters, how long would it take for them to write Shakespeare? The answer is, well, yeah, it would eventually happen, but in a time that's like 10 to the 20th times the age of the universe. Right? There's nothing that prevents all the air molecules in the room that you're sitting in right now from all deciding to, stop being equally distributed and all move to one half of the room and leave you suffocating. Right? There's no rule that says that can't happen other than just probability. It's exceedingly unlikely. Right? 1 in 10 to the 33 chance. And this is not even a big number, right? These are 300 different oscillators. Right? So if we go, so the multiplicity gets sharper around that central value, the bigger the numbers are, right? So we just looked at one where they were where N and Q were on the order of a few hundred, and so we can see there's a fairly there's a distribution around that central point, but you're not going to get to the extremes. But if you make them a few thousand, it gets really pointy. Right, so you're going to be the probability is all really constrained about that central point. And then if we have 10 to the 20th, right, so that's not even Avogadro's number, right? So that would be so like if we had oxygen, right, what's the volume of a mole of oxygen at standard temperature, or mole of an ideal gas at standard temperature and pressure? Sure, one of you chemists. It's like 22 liters.
Yeah,
that
yeah,
seem right?
22.4. Yeah.
Okay, 22 liters is a mole. So this is a milliliter of gas, right? A milliliter of gas would have about 10 to the 20th molecules involved. And so here it says, well, okay, it would be even pointier than that few thousand one, but we can't show the full scale. The full scale would have to be 100,000 kilometers. So it drops to 0 in that first few, the probability of getting this far away from that thermodynamic equilibrium drops to 0 this far away, and then you've got 100,000 kilometers of 0 probability on this plot, right? So just by the virtue of the numbers being really big, we can say how these things need to be distributed without knowing anything else, how the energy needs to be distributed without knowing anything else. You don't have to know, you just have to know that there's a lot of different molecules in air. You don't have to know, like, do they interact? Are they, what's the molecular structure like? Do they obey quantum statistics or classical statistics? You don't have to know any of that in order to do the classic thermodynamics of energy reaching equilibrium. Okay. So questions about any of that? Okay. So now that we kind of have an idea about the statistics, I think that was the last slide. Yep. So the first thing that we want to do is talk about statistics of really an ideal gas. So a classical gas. So I'm going to stop this share and then share so that I can write. There we go. Okay, so the next thing that we have to talk about when we talk about gases, so if we have an ideal gas, or really any gas, we've got two things, right? So we want to figure out, we want to know the probability. Let me see. Of a molecule or a particle to have energy E. Ran out of space to write have. There we go. So the energy, so this is like this is a macro state, right? The energy that a particle has. So we need to know all the possible microstates that would lead to that. So we have, first of all, a distribution function, right? So the distribution function is like those probabilities that we just calculated, right? So the distribution function for, the number of heads you would have would be, or number of ways to get heads would be 1, then 10, then 45, then, the other numbers that we didn't calculate. or the distribution function of all the different ways for that energy to be shared between those two. Well, really within the Einstein solids, it would be the probability of a particular molecule having a certain amount of energy. All right, so that distribution function we're going to call f of E. But that also depends on the degeneracy. All right, so if you remember degeneracy, I'm running out of room there. Let's erase that. Right, so the degeneracy is the number of different ways that you can have that energy E. Right, so if you think about an ideal gas, right, you have and you say, well, how many different ways could I have a molecule have zero kinetic energy, right? Because when we're talking about the energy in a gas, it's the kinetic energy of the molecule. So if I wanted to say, well, for a molecule to have zero energy, there's only one way to do it, right? It can't be moving at all, right? But if I give it a lot of kinetic energy, right? So just think of a ball having a lot of kinetic energy. Well, it could have a lot of kinetic energy by moving entirely in the z direction, or entirely in the x direction, or entirely in the y direction, or it can share some of that energy, you know, partially in the x and partially in the y, right? You have to take into account all the possible ways to have that given energy, right? So that's what we have to say. Why there's a degeneracy, and the bigger the energy is, the more different ways to achieve that energy, right? So you have a probability of a particular molecule having a given energy that's going to depend on the statistics, but then you're also going to have this other factor that's the number of different ways physically to achieve that energy, right? Just by its motion. So so if I'm going to count the number of molecules that have an energy, you know, that are at energy level E sub n, it's going to be equal to the degeneracy D sub n times the distribution function f of E, right? And then our total number of molecules, n, is going to be equal to the sum over all the possible energy levels. So that's going to be the sum over all the degeneracies times this distribution function. Okay, so this distribution function, we'll save that for later, right? So that's going to depend on whether it's an ideal gas or whether it's a quantum gas. They're going to have different distribution functions. But we'll focus first on the degeneracy, right? So, okay, should be a sum, but I hate doing sums, right? I'd rather do an integral. And if there's lots of different states and they're very closely spaced together, then you can treat that sum, which should be discrete, as an integral and just integrate over it, right? So rather than saying, you know, we want to sum over all the n's, let's integrate over all the possible n's, right? So to integrate, we would say, well, we'd have some number n, some small number n, that depends on, you know, what the number density, or sorry, number at that unit energy times that little unit of energy. So that's going to depend on the volume of the system. It's going to depend on, and so then we're going to break this degeneracy into something called G, which is a function of energy. And then multiply that again by our distribution function, which we don't know what it is, and then we're still integrating dE. All right, so this G here, this is called a density of states. So something, okay, interesting. Yeah. So I was just looking at my phone, still thinks it's 9:41 a.m. I don't know why that's the case. Okay, so this density of states is the number of different ways to arrange particles in a particular volume. All right, so that's something that we can figure out independent of whether we have.
What was
Yep.
V again?
Oh, V is the volume of the gas. Right, so makes sense that if you're talking about you know, a volume that's twice as big, you'd have twice as many molecules or particles. So,
What if
so yeah, go ahead.
what if the volume is like a function of radius? Let's say, like it has some sort of density, like
A volume of radius of what?
So, like, let's say volume is not constant value. It's like a function of something.
So
Sorry, that would be density. Never mind. Never mind.
okay. Okay. So I'm trying to see. Okay. So let's to make our lives easy, we'll put our gas in a box, a cubic box with, so then our volume would be equal to some length cubed. Okay, so then we're going to have a wave function for a particle in a 3D box. Right, now we did last semester, we did a particle in a box, right? It's going to have a sine function, right? And then a particle in a two-dimensional box, you just say, well, you have a sine function that has to fit in the x direction, and then one that has to fit in the y direction, and then you'd also have one that has to fit in the z direction. So our wave function is going to look like psi of x, y, z is some normalization that we don't care about, times sine of, so we've got an x, n sub x times pi x over L times sine of n sub y times pi y over L, and then, sorry, I ran out of space, but you should also multiply by a sine of same thing for z. And sub z pi z over L. So if we have a non-relativistic particle which is a going to be the approximation that we take here. We have energy is equal to P squared over 2m. But P is a vector, right? So that's going to be 1 over 2m times the x component squared plus the y component squared plus the z component squared. And using this, so these are sine functions, right? So the wavelength is related to the momentum using the de Broglie formula. That gives us h squared over 8ml squared times n sub x squared plus n sub y squared plus n sub z squared. So we can treat this, you know, we had a vector for the momentum, but we can treat this like these are components of a vector for number, right? So we can just call this n squared. So that's going to give us that energy is equal to h squared over 8ml squared times n squared, which is just the particle in a box formula, I'm realizing. Right. So, so this is technically discrete, but we can treat it like it's a continuous thing because those points are so closely spaced, right? So what we're going to do is try and figure out how many particles would be in this box would be able to have this particular energy. All right, so that's our, so I'll write that down.